Okay, so thanks a lot for the invitation for the first speaker of this week. So I will speak about, so you can see from the title, science data constant, anomalous magnetic factors, and alpha coefficients. As you can see, are topics which apparently are from different fields. You will see why there is a connection. So let me start from some. So these lectures are done in this way. I will start from some general ideas, and then I will go more and more into technical details. So we'll see how much can go in deep things, but I don't want to start with something technical. Let me say some general motivation. So let me recall some basic stuff. So what is the standard model, which is actually the basic theory that we have for reality, and it is a relativistic quantum field theory, so it combines. So I don't know exactly the background, so if I say something obvious, tell me. If I say something unknown, tell me also, and so I don't know exactly the background, so it would be general. So it combines, it's a basic description of reality, except gravity, but okay. So there is this famous description of forces mediated by bosons, which are the gamma, the W, and the Z, and the gluons, and then the fermionic particles, which are quarks and leptons. And then, I mean, there are several theories assuming that there are a more basic description of reality, but they are really questionable. Instead, the standard model is really the basic and sure one, which is confirmed by experiments. In particular, there is this famous experiment of the anomalous magnetic moment, which is one of the most impressive confirmation of the theory. For instance, it is considered the best possible confirmation of a theory ever reached in the history of physics. So you can see I think the most recent results. I mean, the first line is this experimental result, and then you say 0.01159652118 and so on. This has been computed by Penning Traps, is a condensed matter experiment. And the second is the theoretical computation, and then you say 0.0115965. So the agreement is up to almost the 13th digit, so it's something really impressive. So in fact, I mean, if you read the book of Feynman, Quantum Electrodynamics, there is this famous sentence: "At the present time, I can proudly this is Feynman." But of course, at that time, the precision was much worse. But anyway, it was very good. So this is Feynman speaking. At the present time, I can proudly say there is no significant difference between experiment and theory. To give you a feeling for the accuracy of these numbers, it comes out something like this. If you were to measure the distance from Los Angeles to New York, to this accuracy, it would be exact to the thickness of a human hair. So that is the precision of this theoretical prediction. So that is really impressive. That must be, I mean, not forgotten. I think it's one of the best confirmation of relativity and quantum field theory, because it's not qualitative, it's really quantitative, it's numbers. So it's something really impressive. So of course, it's the most perfect agreement in the history of physics, and also there is an active research for finding some discrepancy of some digits. In fact, in the case of this the electron, but you can make a similar measurement for the muon, they found some small difference, and then now building some. They're spending billions to construct a new ring just to understand if these discrepancies are true or not. Because maybe if there is really discrepancy between theory and experiment, maybe this is the hint of this kind of new physics that want to find. But of course, it's very difficult to find because it's to understand, because it's very small, very small discrepancy. Also, why it's so interesting this quantity? Because this number, I mean, depends on all the details of the theory. So if you will see in a second, it depends on the interaction of all the basic forces. So if there are new basic forces, you will get new contribution. That's the point. So it's something which is really depending on really the structure of the theory. So it depends on the quarks, on the mass of the quarks. So it depends on a number of things. So if the theory is wrong, you will see. Okay. So what is the, which is the computation at the end? At the end, the computation is done in this way. There is a part, as I said, there are these three forces, the electromagnetic, weak, and strong. Gravity is left out. So usually the electroweak part is together and it's perturbative. While instead the QCD part, the strong forces is a smaller contribution and non-perturbative. So I will focus on the electroweak. So this electroweak is a series in alpha, which is the fine structure constant, which is a small quantity. So it's 1/137. At a certain point, so you know, this is the famous alpha, the fine structure constant. It's almost 1/137. For some years, people, maybe important people like Iraq, and so there was assuming that this number 1/137 was some significance. Now we don't think it is significant, because there is no way to derive this. So anyway, the experimental value of that is is small. It's smaller than 1. It's 0.01. So this justifies a perturbative approach. Okay, so you can try to write it as series. And the prediction is done truncated the series at a certain order. So you truncate 1, 2, 3, 4, and so on. And this, it is the largest contribution. So this is so you can be surprised that there is only one coupling, but that is the famous unification of strong, of weak, and alternating forces. The contribution of the weak forces, the nuclear weak forces. So the weak forces with a capital W. You know, the weak forces is expressed still on. Okay. So one can say yes, of course. So now suppose that we can compute really accurate with an accurate way this coefficient IAM. So the point is then which is about if you want to make this really a comparison of theory with experiment, we need to know the value of alpha. So which is the value of alpha? So you need another measurement with giving you alpha, and then you can check the prediction of the standard model. Okay. So you have to measure separately alpha. So in fact, I mean, so alpha, for instance, alpha could be measurement from non-relativistic quantum phenomena. So typically by condensed matter experiment. So now, depending on which one is the best measure you have, you can use this argument as a computation of alpha or as a prediction of a standard model. For instance, if you believe blindly that the standard model is correct, then you can use this formula and experiment to derive alpha and to compare with the experiment in condensed matter. Or if you believe that the experiment in condensed matter gives you the perfect value of alpha, then you use it to check the experiment, the standard model. So in fact, up to recent years, the geomagnetic factor was the way in which people was computing this alpha. Now instead, this prediction is used for predicting for checking the standard model using the alpha. So one can say, well, but how we can compute alpha in condensed matter, which is at the end, condensed matter is something dirty. It's not like quantum field theory and high energy physics, in which there is a small number of particles. Something which depends on the material, depends on you have a solid, right? So metal, something like that. So it depends on a lot of parameters. So how you can extract from a material some information on the deep physics, I mean, on the physics at the most fundamental level, because it depends on the material constant. It depends on the lattice. Any physical quantities will depend on a lot of parameters which we don't know. But the point is that there is a number of phenomena in condensed matter which are expected to be universal. They are expressed only by fundamental constants. So that's something strange. So usually in condensed matter, you have something which depends on all the parameters of a metal, for instance. A metal depends on a lot of things, on the forces, on the molecular structure, on the lattice, and so on. But some quantities is expected to be universal. So it does not depend on nothing except fundamental constants. So in particular, the optical conductivity of graphene is expected to be pi over 2 E square over H. Exactly. Or the all conductivity is N H square over H. Exactly. Okay. All the other quantities depends on the metal, on the material, but not this quantity. This is what people expect. So you can, if you measure that, then you can derive alpha, and then you can make a prediction for the geomagnetic factor. So depending on which, on what you really believe, it is more. You can use the geomagnetic factor to check the standard model, or to derive alpha and to check this hypothesis of universality. That depends on what you believe. But anyway, you can have a cross confirmation of both things, universality and the standard model. But that seems strange, right? So let me say something which is at the basic of all the lecture I will give here. So that is something which was understood something like 40 years ago. But it's something very surprising. So the anomalous magnetic factor regards the properties of quantum particles at relativistic energy, so Dirac particles. So where the relativity is there. Instead, the transfer coefficient, like all of the conductivity, regards quantum particles at low energy, which are described by the Schrödinger equation. However, they are described by similar mathematical objects, partial integrals, which we want to introduce, and in certain cases, there is an emergent Dirac description at low energy. So even the interaction of the lattice in certain metals produce a sort of regularization of the quantum system. Okay, so as this is the mathematical conference, so let's go to the mathematical problem. So this is a very stringent test, but I mean, if you really go deep into the questions, it's based on assumptions. Okay, so the assumptions are very crude assumptions that are still there to decades. And then it requires a mathematical understanding. So first of all, the series, so I said that this G minus 2 is obtained truncating this series. So this is what physicists usually done. I mean, you have this series and then you truncate. Of course, you need convergence, but it is known that these series are not convergent. Sure. So, not only they are not not convergent, but even not asymptotic. Asymptotic means that at least you can give a change to some and so on. They are not asymptotic. This is a phenomenon called known as reality. So if you really remove all cutoffs of the theory, you will get fixed models. Okay, so that's the proved for the proof by Fredrickson for being written strictly for the 5-4 model. For the 5-4 model is essential in this is the text. So it's essential in this standard model. So it was proved in Dick written than 4. Then recently Eisenman and Domenico Penn finally proved for people to fall. So sure that, but it was already well known that was the theory was trivial. So it's possible. So it's possible that trivial means that you get G2 should be 0. G minus 2 should be 0. And if you remove all cutoffs, the only way is to get a non-interaction theory. So if you get an approximation to 0 of something, and you can do something fresh. So how is possible from keeping a series which is not convergent to get a result in agreement with the reality? One could say, well, okay, so a blind mathematician could say, well, okay, it's impossible, that's it. But then, of course, but the numbers are the same. So it's something to understand, okay? So the situation, in fact, is very similar to what happened at the beginning of physics. I mean, if you read the objection which were done to the physical fluxion of Newton by people, there were mathematical objection on these fluxions and so on to Newton. They said, oh, this is mathematical meaningless. On the other side, Berkeley said, okay, all this way of computation of Newton is meaningless. On the other hand, the results are correct. So, the kind of sentence you get the truth is not the reality. I mean, the situation is typical in physics. I mean, you have the results, some operation will give you the correct result apparently, but the mathematics behind is strange. So there's something simple to understand. So the other question is, for instance, are we sure that they are universal? So this quantity here is really pi over 2 or not? Or there are some small things, I mean, there are corrections. Okay, so this is another question. So theoretically, this universality is found, for instance, with the topological arguments. Typically, these topological arguments are based on non-interacting systems. So instead, in this case, there are interaction, disorder, and so on. So are we sure that there are no corrections? So if there are corrections to this transport coefficient, then the value of alpha will completely wrong, and so on. So these are two basic questions. So let me say some small questions. So first of all, they seem different, this kind of question, but they can be analyzed by the same mathematical technique first. And second, so once that they've said that you can analyze this by the same mathematical technique, well, you could ask, why for these quantities there are no correction, and instead for this one there is a series. So why in this case is a series, and the other case is a number? It's a number, I mean, they're all numbers. So what I mean is that in one case you have a series equal to something. In the other case, the theoretical prediction just pi over 2, not an expansion. So why? And also that should be understood. Okay, so these are examples of basic questions which are there since I don't know, half a century or even more. I mean, is the famous problem of quantum field theory, that you get this computation which apparently are meaningless, but then the results are correct. So I mean, people are struggling over that since the focus. Okay. But as I said, there is no problem on this. For instance, after Newton, it takes 200 years to arrive to Cauchy and understand the calculus. No. So now it's really a needed situation for mathematical physicists. I mean, there is a theory which is working, mathematically strange, it's perfect. I mean, you will be not Einstein, but you can be, I don't know, Lagrange or Cauchy or people like that. I mean, you must content yourself. I mean, everyone now wants to be like Einstein. Einstein is good, but it's not bad to be like other people. Okay. Okay. So let me say something about this experiment. So let me recall you this graphene optical conductivity. So you have this, so the graphene, I don't know if you know what it is. It was given to it the Nobel Prize in 2010 to Geim and Nosopoulos. It's essentially a bidimensional material. That is, I like very much because I don't like to spend too much. So I like an experiment that doesn't cost anything. So essentially it was done something like Friday evening. For, I mean, Geim and it's a professor in Edinburgh and was, no, sorry, in Scotland, but Friday evening was doing some crazy experiments for joke with students. And he wanted to invent the super glue. I mean, he wanted to invent the glue to make like Spider-Man and climb the wall. Okay, so he wanted to invent this super glue. In fact, he won before the Ig Nobel, before getting the Nobel. It was invented. So the glue, he invented super glue. This Spider-Man law doesn't work. But he had the idea to stretch a sort of graphite with this super glue several times to get the bidimensional material. Okay, so you get what is carbon. Carbon is the inside of a pencil. So you put the inside of the pen, it takes the inside of the pencil, you just stretch it with the glue in this way several times, and it goes at the end a really three-dimensional material, which was done by Nonico Lassi. So this is what is now called graphene. So it was an experiment which was essentially called. And then it got immediately Nobel Prize because people were not believing that it was possible to obtain a dimensional material. Okay. Then, in particular, so this is graphene, and this is carbon layer. And you can copy the conductivity, and in general, the conductivity is done in this way. I mean, it was very interesting because these three-dimensional materials were very much studied by mathematicians in the past, in the 60s or 70s, and they know very well that the conductivity was that, but was sort of like the in modern two-dimensional sort of theoretical game. People do not believe that was possible. And people were very surprised that it was possible to really realize. Okay. Then the It was known that you get this pi over 2, but people was believing that there were corrections due to the many body interaction. Okay? And then people was trying to compute. There was a lot of prediction on physics about this many body interaction, this Q1, Q2, and so on. For instance, they get infinite, was impossible, but they get something like 1 plus infinity, that was bad. And then they usually in physics, if you get 1 plus infinity and you believe that the object is finite, then you say, but that 1 plus infinity is simply the expansion of 1 over 1 minus infinity, so you get 0. So the prediction was just 0. Okay? So there was a lot of prediction about it. Then people was very surprised when the experiment was done. This is famous experiment done. And then they found that there were no difference between these numbers. So there was all these C were 0. So this is the theory, the green, you see this is the theory in this experiment. So the result was pi over 2. So even if you put the interact. So this means that this C were exactly 0. This is not obvious because this was not obvious because U is big in this case. In the case of graphene, U is greater than, it's almost 1. So it was strange. So instead, sorry, I repeat, this is the result without many body interaction. If you put the many body interaction, in principle, you have a C. Then you can try to compute this coefficient, and you get several numbers, because it's very large. And then at the end, but then the experiment was done, and they get exactly pi over 2. So this is an example of universality. There are no correction. So this was a typical universality found first experimentally. People, because it's difficult to see which objects are universal, which are not. Okay, so you get exactly that. I mean, at least with precision. Okay, so this is an example of universal phenomenon. So this is pi over 2. So of course, now the point is really pi over 2 of this Q1 are exactly 0 or not? I mean, the theory, you need the theory. Yes, there is a small difference, but no, that's the experiment. So anyway, if you want, U is also 1. So if Q1 is a number, you will get something here. So it's a really range experiment. So the other example is the famous, I think there will be other talks about that, is the Hall conductivity, okay, which is instead still bidimensional material, but the transfer conductivity. Again, you should have this quantized value plus correction, but at the end, one believes that there are no correction with the many body interaction. So this is the experiment you see that, but all you don't see effect of this many body interaction. So without many body interaction, there is a topological explanation, but which is absent in the case of graphene. In this case, with interaction, we will see. Okay, now let's go to this. So these are many body example. Now let us come again to this perturbative expansion for the Germanic factor. So now I write it more explicitly, showing you exactly the coupling of the electromagnetic forces and the coupling of the weak forces. But you see there is a relation between the electromagnetic coupling and the alpha and the weak coupling. And this theta is called the Weinberg coupling. It is a number, it's an experimental number. It's the ratio of the W and so forth. So due to perturbative renormalizability, I and M is finite to order. So that is not obvious result, which takes in physics something like that. I mean, to get this sentence, I mean, it's the reason why people introduce the Higgs boson, introduce the W, introduce the Z. I mean, this is not obvious at all. The A and M are finite to all order. It's the famous proof of Toft that this is true. It requires the Higgs that was covered and so on. Usually, this N M M could be not finite to all orders, but it is. This is a very, this property is hard to prove, even order by order. So a language specification, people speak about results order by order if they want, because this coefficient in quantum field theory can be diverging. So people speak about finite order by order if you can prove that they are finite to all order. and non-perturbative result if you can give meaning to the field. So this is the terminology. Okay. So let me recall the history of this computation of numbers. So the first computation was done in 48 by Schwinger. It is, I think, in the tomb of Schwinger, the formula, alpha over 4 pi, the triumph formula. So this 1 over 2 is the reason for, is the birth of quantum field theory in IMF. Maybe, I don't know if you know the story. I mean, there was found this discrepancy of the G between the Dirac result is G equal to 2. Was found a small difference with respect to the result G equal to 2 in the experiment. And then it came out the famous paper by Schwinger, which was able to prove at first order that the contribution of the is 1 over 2 alpha. But it was done in the first year. Then, of course, there is all the stories that Schwinger did this computation in a very complicated way, then Feynman find this way with final graph. Then it's interesting because the second order was computed by Karpus and Knoll in the 50s, but the result was wrong, and that was very bad. And the correction was in Sommerfeld. So here there is also a nice story about that. In the paper it's written that the computation was done by 2 groups independently, and the result was the same. It was in agreement with the experiment. Then later, the experiments were redone. It was found a difference. And then it was found an error in the computation. And then people asked, how it's possible you did the same error? And then they had to admit that they checked the graph, and then what is so, but I mean, if you have if you look to the paper, you understand why this happens, because there are, I don't know, 40 terms. You are very tempted to ask a friend and ask a deal. But they said that it was happening. But then now there is this correlation which is not correct. Of course, you can say, okay, that's a stupid thing, but I'm not able to run all this computation. It's very something like, I don't know, 200 integrals. You know, where. Anyway, this is that. Then A3 Laporta, and then here start with up to the 5th order. Unfortunately, even here, but from here on, no one is possible to recheck this kind of application. They are done. These are done numerically. This also is complicated. It even did so this is okay. Enough to understand the Schwinger stuff. So what about the week? The week was computed by Jevick and Weinberg and Altarelli and Cavibo Miami. Then you get this other result. So because at the beginning there was no new. They put only the electromagnetic contribution. Then they add this contribution. In particular, you get this. This is the contribution of the Z. And you see why it's less important, because that is very important. That why this one is a pure number. So the electromagnetic contribution is really a pure number, 1 over depending on alpha, which is an dimensional factor. This one depends instead of the particle. So the electromagnetic contribution does not depend on the particle size. Instead, so it's the same for any electron muon. Instead, for the width, you get this m over n. So it depends on the mass. So this is the reason why people are studying the muon, because in the muon case, the m over m is 10 to the minus 3. So it's quite different. Anyway, this is important to remember. Okay, anyway, this is a very small contribution. So of course, now the problem is how it's possible that truncated in this way, how we can bound the rest as this Okay. So let me say also that I was mentioning this concept of universality, which appears. Of course, universality was, I mentioned universality in condensed matter, I mean, in this case. So this is not completely, so there are 2 different kinds of universality. In this way, for the QED, depends only on alpha, but it's approximate, because of course, if you put other forces, you get some dependence on the time of the particle. Instead, this universality in condensed matter is believed to be exact. These numbers are independent on all the possibilities. So universality appears also in statistical physics. So it is a place in which appears for the first time. So in fact, it appears first in not in condensed matter, but in classical statistical physics. So in particular, in the exponents of the Ising model. For instance, these are famous experiments which were done for the Ising model to dimension. There was some index which are called critical index. Then appears to be, people were very surprised that in different materials, you get almost the same result. So that's very strange because all these objects are completely different physically, so that they are different molecules and so on, but they have more or less, with the same error, the same result. It is believed that they must be equal to 1 over 8. It is believed that this number should be exactly the same. But it is very strange that you get these materials are completely different, but the exponents are the same. So that's not the same thing. It's the example of there is also a notion of marginal universality. So these are numbers. There are other cases in which they verify relation between them. Particularly, you can have, will come back. So in this case, these exponents are not numbers, but are universal in the sense if you come to one of them, you can predict exactly the other. So I mean, this again, some prediction which are without parameters, essentially, this and that. So this universality stuff is something also very, very interesting because it allows you to make quantitative predictions. So if you're materials, you don't know all the material parameters. Depends on a lot of things. But these objects are exactly without parameters, so you can make a prediction. So this is another stuff. Okay. So now, okay, so let's enter more in the theory. So first of all, I will describe all these phenomena on a lattice. Okay, so this means that I will not put on the continuum, but in the lattice. This is a drawback, of course, but this is the point of view I want to take. So in the case of condensed matter or insulators, the lattice is a physical ionic lattice. So you know all metals can be described by lattice of ions or something like that. So it will be in the discrete. In the case of quantum field theory, of course, it's known, not known, which is the deep structure of space-time. So I will assume anyway that I will put a lattice, and which in technical words is a cutoff. I don't want to remove it. So of course you can say, well, but then you will have a dependence on the lattice. So the point is that you want to have bounds so that the dependence on the lattice surface is the correct, not the it's called the effective quantity. So you put a lattice, but then if this lattice is not visible with the elemental precision, you can say. Okay, so this is also a famous picture by graphene. So as I said before that the mathematics for this condensed matter system and for quantum theory is similar. So for example, this is the energy of this graphene. If you look to this point and you enlarge, you see that the special relation is almost the Dirac. That's called Dirac material. So I mean, why people is was very happy of this dimension. Material theoretical people is that they are sort of simulation of quantum field theory in the case, and without structural acceleration. This is like Wade to the graphene, for instance, it's like Wade to the block. So you can make it really, it's a sort of simulator of quantum field theory, so you can really check the quantum field theory on low velocity. So this is one of the things. There are two reasons of that. One is that these materials are very similar to quantum field theory. So technologically, of course, they have properties completely different with respect to usual materials. They are here as well. And theoretically also it's very interesting because you can check the prediction. Okay, so let us come from the basic objects. So which are the basic objects of the theory? Well, they are called Euclidean correlations. So these are the basic, all these kind of systems and problems can be studied, at least in the approach I will describe, in terms of objects like that, so which are called Euclidean correlation. So X are points on a lattice, so I will put myself on a lattice. I don't want to try to define the functional interval directly in the continuum. I will put everything. So these are discrete. Spin defined is a Gaussian measure, and V is a sort of phenomenon. Okay, so this is the basic structure of this object. And then there are two cases, which are these cases by myself. Fermionic or boson. So these are, in a sense, it's a work different from the Hamiltonian work, in which we have operators, and from the classical work, in which we have the statistics. Here, the basic objects are this kind of thing. It's more close to probability, or correlation of. So in the bosonic case, the definition is easy. So phi is the Gaussian, is the function over R, so goes from minus infinity to plus infinity. X is the lattice, so it's a point in lattice. So P in the field, simply A is the positive matrix, of course. It's a very large matrix because X is an index, but don't forget that X is an order. The number of points is an order, but if you put at the beginning everything is fine. And then, for instance, the famous phi-4 model, V is a polynomial. Okay. So you have, it's finite, but the problem is that the number of variables is very large. It's L over A. Over A, where L is the length of, the lattice is the box, L by M, so the length is L and the depth is A. So you will have something like L over A variables. Okay, so of course this goes to infinity using any case. A equals to 0 and then master. So in the one-dimensional case, it's simply something like e to the minus squared minus 1 is 4. So a typical example is this one. This is the zero-dimensional case. And of course, already from this case, you see that you will have problems expanding in lambda. So you see immediately here why expanding in lambda as in Feynman graph you have problems, because if you try to, this of course is not analytic in lambda, so you don't want to expand, you can't expand, but Feynman graphs are expansion. So you already from the zero-dimensional case, you see problems in the expansion. But if you change your sign, then it's serious. So the fermionic case, instead they are Grassmann variables, and we say what they are. I will be focused more on Grassmann variables. So they are anti-commutative objects. You will see there Grassmann measure essentially functions of the Thematic, nothing positive. So at the beginning, in the finite dimensional case, this thing poses no problem. The problem is when you want to send so the prototype is of this Grassmann variables of Grassmann integrals was done in the what is called Fermi model, which was the first model for weak interaction. It was then replaced by the standard model. But the first model was the model proposed by Fermi, which we can do also in terms of Grassmann variables with a similar to this phi-4. I will enter more. I want to just give you an idea of what finite dimensional integrals are. So when you have in the finite dimensional case, these objects are all three. For instance, in the one-dimensional case, in the boson case, they are just Riemann related, something standard. In the fermionic case, they are even simple because the rule is simply this. The size 1, so for instance, this integral is lambda, but this is really something completely trivial to have. The problem is when you want to have infinity. Okay. So now tell me some terminology. So the L going to infinity is called the infrared problem. So this is, if you are not familiar with terminology, I will take some minutes to explain it in order to remember this what we talked about. Here going that people continue to use. Of course, infrared and ultraviolet are names of recalling the energy. So infrared is low energy, and ultraviolet is large energy. Large energies mean small distances, and more energy means no. So if you are the limit n going to infinity with A6, it's called the infrared problem. That is the problem in which you are interested in condensed matter. You want to consider lattice to the fine stress, but of course the material is completely long. And then you want also to send the species zero. The other limit is set A going to zero is the characteristic is the problem you are interested in quantum theory. You want to send the length zero, so you want to consider very high energy conditions. So you have two limits, and there are two different problems. If you are only interested in condensed matter, you would simply consider this L going to infinity. If you really want to consider the ultraviolet limit with the infrared cutoff, and then you consider N go to zero and L finite. The real quantum field theory, according to the action, would be to remove both L. Okay, so that's something. So this is just to put a framework on the problem. So there are these functional integrals which are simply finite dimensional, but then you want to take this or the infrared or the ultraviolet or both. So depending on the problem you are interested in. If you are a condensed matter theory, you are interested in infrared. If you are interested in if you are high energy physics, you can be interested in ultraviolet. If you are mathematical physics, you are interested in both, in what you can do. So you could typically, if you have an object like that, you could the naive thing to do is just to expand exponential, right? Which is not a good idea, but it's a naive idea. You could say, well, at the end, this field phi is a Gaussian measure. So of course, you know the correlation of a Gaussian measure is given by the Wick rule at the formula. So you can try to expand this into the minus b. That's a possibility. So if you do that, it will appear the covariance of this field. The covariance of this field is called, in the physics language, the propagator. And then now, again, you can distinguish two cases. Another application. So it's model with the power of decay of G for large distances are called critical of mass. What critical refers to, so now there is a terminology problem because these objects are used both for statistical physics, condensed matter, and quantum physics. So the language reflects the different physical units, but the mathematical problem is the same. So if you have a power law decay, you say critical, which is the name in statistical physics, or mass, which is the name of the quantum physics. There is no mass or instead, you are exponential decay is called massive or so of course the critical case of massive is more critical. Okay, I will focus here on Grassmann integrals and I will see how much I can say. So as I said, they are central in modern physics. So for example, let me go a bit more in the case. For instance, condensed matter conduction electrons in a metals are reduced of interacting kernels. The equilibrium correlation can be written in terms of Grassmann. In this case, your space-time now the finite, so there are some details which is different in condensed matter quantum theory. So in condensed matter, you are giving beta at one dimension, but one dimension the length of the side is beta, which is the inverse. So the quantum theory is only for considering the time property. Then of course you can do the limit L to infinity and 0 10%. Now the side of the box is the quantum theory you have in the 4-dimensional space. You condense the matter always the same, but one dimension you can imagine a time, but then the length of the box in the selection is inverse. And you get this you get the partial integral by the Gibbs phi. It is especially Gibbs phi. the trace of into the manuscript age, and then you can show this effect. So it is directly done in this way. The same is in statistical physics. As we see, we see in statistical physics that models can be written in this way. In condensed in quantum field theory, it's more subtle because then you have a formula that's called the Feynman integral, in which you have the I. Then, of course, the I is dead. So people prefer to study what are called LCD okay? In which you replace the time with the matter time. So you go to the important space. And then at the end, you will get pattern. And then you have some. Of course, yeah, of course, here now there are no discussion about that because of course, according to the common reason, the construction of a quantum field theory would consist in proving that you can take the limit and take it to A equal to 0 and verify the state of action, for instance, the observable Sherry action, which imply the Whiteham action, and then in this way you will assume in the field. That is possible. At the moment, it's considered to be possible only in lower dimensions, but of course you can consider instead an Euclidean effect in quantum theory in which you can take A fixed and then you get weaker results, but apparently it's the only way you can construct a four-dimensional theory. On the other, okay, I will comment about that. I mean, on the other hand, it seems now that the requirement that there exists a quantum theory for dimension is too much. But in a sense, there is no problem at all about that. Because all theories are respected. They are true up to a certain energy state. So we don't know what happens to extremely high energy state. So there's no reason for it. I will comment about that. It's an interesting point that seems to me that in the mathematical physics community is not completely received. Now the point of view is that also the standard model is respected. So here clearly there is no reason for it. But this formulation of Weissman was too strong. That's I think in the physics community it's given for granted. Okay, so I think that the theory of subfunctional interest is given by many physical domains, and then you have different. So maybe. How much time I have? 10 minutes. Okay. So, now this was a very general introduction. So I introduced a lot of concepts and work, provide the info and so on. So now let me consider this crucial concept of breadth and depth quantity. That's important. So first of all, you can, as I said, you can try to adopt a simple-mind approach to compute this functional integral, which is expanding into the field. Okay? So, as I said, you come back here, then you say, okay, of course, this integral even low-dimensional case, but you do, but this is very small, so you can try to expand. Right? This you will get in period of time. You can copy it explicitly. I mean, it's even not so easy to copy. I mean, you have to make a lot of computation to compute, it's order. But then you will arrive. So now you will get a number of problems because you will get, if you expand and then you take the limit, you will get integrals which are there. Now in this, you get integrals. So these infinities are, again, these integrals prepared both for, the integral from the k for the both when k goes to infinity or to 0. Like integrals or one of the, it's always best. If you integral from minus to plus infinity, that's always best. So you try it, it's kind of flat, it's kind of small. So you get the worst possible integral. So in fact, it's not a miracle that people was not. Like before the war, for instance, people Was impressive that by this apparently meaningless object, you can start numbers. So you have two integrals which are diverging. So, but the origin of this divergence is very different for, so now it's kind of simple. You get people in the simple mind when you get it simple. But then if you look things about or you understand that in condensed matter of statistical physics, this divergence means simply that you are expanding, it's a mathematical problem. It means simply that you are expanding around a point which is, I mean, the perturbation theory works only if the correction are close to the unperturbed system. But of course, there is no reason for which the interaction doesn't change completely the game. Maybe we try to make an example. That is the simple example. So suppose that you know that, maybe it's much simpler to understand that by a clearer example. Suppose that you have the correlation is something like k squared plus m squared, okay, without interaction. Lambda is the interaction parameter. And typically it's the mass of the critical temperature. So suppose that at the end the interaction simply change the critical temperature with the finite cost. So it would say that it would be this would be a trivial change. The behavior of this object with them would say the interaction would say simply that instead m squared you will have m squared plus lambda squared. But of course, if you expand in lambda, then you get this. So now suppose that you are considering a theory in which n is 0. Then of course you will get a lot of divergence. So simply you cannot do that. So this works only if lambda over n is smaller than 1. But on the other hand, here you can put n equal to 0 without n. Suppose that this is the result of the integral. Then here you can put n equal to 0, but here not. So if you are doing that, you will get infinity at space. You can see the result of this. So this is a typical error on the surface. So the error here is more mathematical. You are expanding around the point which is not the correct one. Instead, in quantum field theory, no. Quantum field theory is more these divergences are the ultraviolet one. It means that not a simple phenomenon. Not obvious. So this is a first difference. So not all the infinities are the same. Condensed matter are essentially due to, they are not real in a sense. Instead, in quantum theory, these infinities are real if you remove also the lambda. You will see more clearly. Okay, unfortunately, so this is something happens typically in physics. People started to face the more difficult problem. So physics started to consider the worst possible theory is quantum mechanics, which has all kinds of problems. So it's very difficult to disentangle the problem in quantum theory. There are several problems in quantum mechanics altogether. So it's a miracle that physics is something, and now we understood that the starting point was maybe the worst. So even if the paradigmatic theory, quantum electrodynamics, is still very not well, and it's not well understood at all. So let me recall to finish this introduction some statement of the results. So they started with this quantum electrodynamics. Then there was this was the name, data, Schwinger, Feynman, and Dyson. And these three guys, the Nobel Prize and Dyson. But at the beginning, Feynman didn't write the paper, Dyson wrote the paper. So at the beginning, they were called Dyson, and then Dyson said, I was thinking, Feynman told me that it was lazy to write the paper, so I didn't know that. I don't know if you know the story, they arranged a car and got to California from the US, and then Feynman was speaking and Dyson was like, what is the point? You have an observable, and then I finish with this. You have an observable, which is the pair charge, and then all this field. So you expand this to the B. So this is what you expand in this B, and then you get a field to the B. And then all this field. Then you introduce a regular equation. Then you do the same. So of course, this B reverses with lambda. And now you say, well, the real charge is the dress is also an observable. It's not the lambda. What we really call the charge is also an observable, which can be written as a series in this way. So we can invert this. We can invert this relation. And now we call this stress. Now we write P of epsilon B of lambda epsilon S of lambda is a series in this series. And the miracle is this is the sign. This is the idea of it. So why is this a miracle? Of course, the point is that this direction, we say this is the method. In other words, the pair one equals two, and you want to because you say this stuff. Then what you real measure is one. And then you want to expand everything epsilon direction, and then these objects here now are in production. So this is the miracle of the communication. Maybe I repeat you as an important point. Like, epsilon B is the perturbation parameter. So you expand in that. And then all the coefficients are zero, are infinite. Then you regularize, so are finite, but then, of course, they diverge in this. Then you say, but among the observables, there is also the charge. So we are not measuring the bare charge, but this directed one, which is also written in the same way. So of course you can write epsilon directed as function epsilon B. Then you can invert. You can write epsilon bare as a function of epsilon direction. So and the point is that now you forget this, but you say epsilon bare is something you measure. And that is the parameter you have from the. So now you re-express everything in terms of this epsilon B, which is what you measure. And then the miracle is these terms are all final. So it's only by these properties you can make prediction. Okay, but of course, I mean, there are two problems. One is the problem of convergence. One is the problem if this is true to all orders, because of course this is found in fathers of the notation computes only as first and second order. Now, the very difficult problem is this procedure holds and says this to all orders, for all CI. That takes something like 30 years to be proved. But then means the theory is renormalizable to all orders. But then again, this is nothing because once you have proved that these coefficients are finite, then you have to prove that the series are convergent or have some meaning. So this is the problem of the non-perturbative. And now the normalization group is the modern way of implementing normalization. So this is the very old way to explain normalization, and now this way I think has been modified by Wilson, which introduced the concept of normalization group. I'm trying to explain. Okay, you find it. Huh? Okay. Okay, so what is a normalization group? So I finish with this. So this normalization group. So this was the idea of the 50s, we just did use it in a way. We started from the graph. The idea of Wilson was completely different. So Wilson, it was very much influenced also from statistical activity. But people which are still doing the PhD, Wilson didn't talk with his professor for all his thesis. Didn't look at all. So, I don't remember, but what now I remember that was some. This guy is important. I mean, this happens what? I mean, you can try to do that. It was very research problem. Why they say example like that? I mean, they produce a lot of interesting stuff. So the thesis was completely different from what we can do. That was the idea to do. And then it took, I mean, 20 years to understand what he was saying. Still now, it's not very good. So what is this idea of weeks? The idea of weeks, and now I tell you how we understand it. Okay, so the idea is this one. So that is the modern way. Okay, look to the paper of weeks in first week. We understand it this way. So now I said, so let me try to explain things to the idea of weeks in 5 minutes. This is not obvious. So now, recall that we want to study this, and this being defined as the covariance, which is called the propagation. So at the end, if you expand this, you will get integral of this G, the propagation, the covariance of this function, which is a function, you said that it's the logic area and stuff. So if you do it all together, if expand, you get solved. What you do that. So the idea is, instead of doing this expansion all together, let's try to we divide these propagators, this G, in some of them. So typically, this G, you will see example in next hour, are integrals of a K of function. Okay, so this is the Fourier transform. So the Fourier transform of K is the momentum. So this G hat is the Fourier transform of this let us write a sum of them. And this GK now is subplot, gamma is a constant, 3 over 1. So K, instead of going to, now we have a finite box, but if you remove the cutoff, it's K from minus 3 to plus. Then it was finite N, that is 3, it was elastic, it's up to 1 over A, but this something is very almost closer to a continuous, almost closer to that. So instead of doing this, instead of writing G, you write G as this sum of them, which leaves in check. So the moment, the energy is between gamma to H minus 1 and gamma to H plus 1. We have different checks for to make the decomposition of the unit. And now you use the trivial property of convolution. Right? You have a measure, the sum of action measures, is a function. So using the integral, you consider then you will try to take the product of two vectors. So you write P the phi, P the phi n, P the phi. When the proportion of Pn means Gn, and where much smaller than it becomes from H to minus infinity up to. So you decompose the source, the sample, maybe there's some, anyway, so you go back. So H, let's suppose G is minus infinity to N, and then you decompose minus infinity up to N minus 1, and then Gn. So G minus N plus Gn is G. Okay, then you integrate the and then you get something which is similar, which okay. So these are steps that you can do, and now your steps are much better than before because now these integrals are in a finite dimensional domain. Typically, it's not singularity. Typically, here we are assuming that the singularity of the integral is in K equals to 0. Now it's a bit abstract. You will see examples. Typically, GK is diverging at K equals to 0. So I'm assuming this. Okay, it's something like 1 over K is 1. Then and now if you GH is between H, so the singularity is outside and K is fire. So this the Fourier transform, of course, you have to consider it multi-composition of the unity, otherwise you have problem. You taking a simple okay. But suppose that you consider a multi-composition of the unity, so this the Fourier transform of this GH will be good. So now you can integrate it again. It's much better. Because you're not quite fine. This is a confidence integration, you get to the answer and so on. This CN, that's the Fourier transform. And then you will get another CN. So this is a mathematical step. In the physical jargon, one says we are integrating out the high degree of freedom. Here you integrate out the high degree of freedom, the high energy degree of freedom, because a K is sort of energy. So you should start from the largest one of the highest. Then you will get that. So what means this? And now you start with the theory in which the energy was arrived to gamma n, and you arrive to this one, which the energy arrives to gamma n minus. But then the interaction is not. So it's the energy force. So this is a very big point. So this is just simple mathematics, but it's a very big point because it says that we ignore not the unique way. That's the end of it. It's a change of paradigm, I would say, even in the way we understand what is the physical law. If you start from a V, you say this is the real model, and then it's equivalent to writing this way. So you say if you change the maximal energy that you consider, you can, it's equivalent up to the modification of the interaction. It's modified. So now what you do now? But now of course you continue, and you integrate the gamma, the Vieri, and go and go on. Then you will get a VH. VH means I'm integrating up to the same H. So now typically this GH has the form here, K divided by K to the alpha. So that is another crucial idea. So if you change variables, G with the cutoff H, which is smaller than that, it's essentially the original cutoff, the original propagator with this the factor. It is the crucial idea. Maybe I will comment more in the next slide. This power is very important. So this fit now, this means that T smaller than H, the theory with cutoff to the H is distributed as the original fit with the prefactor. So the monomial will be similar to the original one up to a constant. Okay. So if it is not always at all, this constant becomes smaller and smaller, this means that when you iterate this, at the end you get the Gaussian theory. So the iteration disappears. So in this way you can construct the theory. If this does not happen, so if the sum of these terms increase, that's also interesting. You can understand which is the real theory, which are the really important kind of. That's the simplest case in which is when this n is negative, then h minus n is negative, so it's a minus. So this means that you start from this theory. So that would be, in a sense, for mathematician will be nice because it's the simplest case in this theory is possible to construct. For physicists, it's very bad because it's just construct. But now the mathematics is a lot better. In addition to that, of course, the easiest case is when you iterate this, the end becomes smaller and smaller. At the end, you get the Gaussian. And then Gaussian is very simple. For physicists, this is disaster. That's why we are introducing it for normal. And even if what I'm saying is not completely correct, because even if you get something, this VH was 0, the parameters would be changed. So even if this simplest case in which all the terms are negative is interesting because at the end you get the Gaussian theory. but with different signs. So that's also myself. Even this case is interesting because the occupation theory doesn't work. So even if all this L here, or even if all this L is negative, then you will get a partial theory with different signs, different mass. So the occupation theory doesn't work. But of course, it's not the most interesting theory. So I can conclude, and then I will return to that. Because this is another crucial language that I want to so again, these are three. These are called header. The sense is yen more. This yen is called the yen is also they are called header. Yen is negative, they decrease. Theoretically zero, they are called one. The theory in which all the terms are, there are terms are relevant are called super-renormalizable. If the trees are called non-renormalizable, and the terms in which the n is equal to zero are called mass. So what means this? So when interaction is irrelevant, it decreases iterating density. So there's at large distance, the behavior is unchanged. If relevant, it's the opposite. It increases, and the behavior is decreased. Or what of course you can do. Okay, maybe I can stop here because this is a very important point. So maybe I want just to leave you with this conversation that I leave you very easy. So the first line is to obtain the changing variables because you have k is the cutoff function depending on gamma and h. So this line here is simply the changing variable. This is very, but it's very good. When you use the propagator with the cutoff h is equal to propagator with the cutoff s. If you change instead of x, gamma to this h and then you use the stuff. This is a simple change of variable. You make a change of variable from k to j to the h in the Fourier form. Then you do. One is CFS. This is simply you obtain this in this way. You start from this. You replace this. You change variables itself. Then you will so the d is from the change of variables from x gamma to the h x to x. And this here gains this on but you have n field. You have n given alpha divided by 2. And the propagator is the cover. So you have n field. When you get given alpha divided by n times n, then this d is the change of variable. And this is called the dimensional, the scaling dimensional. And that is the crucial quantity of this thing. So for instance, in quantum electrodynamics, is 4 minus 3 over 2n. So this is the basics of all the theory. The basic point is to make it very difficult to understand the element marginal. So this means that iterating this monomial decreases or remains. And that is in course a lot of things. But revamp this is that. So physics, you know, here.